Last time we were talking about multiplicity, and the first example that we discussed was the Einstein model of a solid. I'm going to remind you of a couple things that we did last time, and we want to make things a little bit more interesting, a little bit more complicated. If we want to calculate, suppose we have an Einstein solid that has n over 3 atoms, which means it has n oscillators, right? Each atom can oscillate in 3 dimensions. So we can say that we have n oscillators. And let's say that we have q energy units to distribute amongst those n over n oscillators. If I want to know the possible number, this is what we said last time, I want to know the possible number of accessible states, omega of n and q, we can write that as q plus n minus 1 factorial divided by q factorial times n minus 1 factorial. That will give us the total number of accessible states, or possibilities, what we call the multiplicity of this example. So if I calculate it, what we did last time was we calculated it for, it turns out we had 3 oscillators with 3 units of energy. And we calculated the possibilities for this, and we came up with a number. So what we did beyond that was to say, let's do 30 oscillators with 30 units of energy. And when we did that, we came up with a number of possibilities, omega of 30 and 30 equal to 5.91 times 10 to the 16. So for just 30 oscillators and 30 units of energy, we have 5.91 times 10 to the 16 possibilities. That sounds like a lot. You haven't seen anything yet. Let's make it a little bit more interesting by talking about not one system, but 2 systems that interact with each other. So suppose we have the following situation. We have 2 solids. We'll call this one solid A. We'll call this one solid B. This one has n sub A number of oscillators and q sub A units of energy to disperse amongst the oscillators. This has n sub B oscillators with q sub B units of energy to disperse. Now, what we're going to do is essentially explore heat flow and irreversible processes by letting these 2 solids interact thermally. So, first thing we're going to do, we've talked about, these are, we call this the number of accessible states, or the number of accessible microstates of the system. With that, we want to define another term called a macrostate of the composite system. A macrostate is an indication of how many microstates will form the same, essentially the same macrostate, the same macroscopic state. And you'll see what we mean as we go along here. So the idea is these solids, of course, are weakly coupled, and so what we're going to explore is an exchange of energy between the 2 solids. And so let's set it up this way. Let's say that UA, the energy in solid A, UB, energy in solid B, exchange energy, but very, very slowly, so that they're essentially fixed for all intents and purposes. Of course, it still will remain, no matter what, that the total energy of this combined system is the sum of the 2 energies of the individual systems. So we're going to let these guys exchange energy. And let's see what happens when we do, let's take a very small system, then we'll build from there. So let's suppose the number of oscillators in each system is 3. And let's say that the total amount of energy which is, of course, just the sum of the two energies, is equal to 6. So I have 6 units of energy that I can distribute, 5 and 1, 6 and 0, 3 and 3, whatever the case may be. Okay. Let's make a table of what the possible results can be. We can do this for this small number of things. We could certainly not do it for something like 20 oscillators or Avogadro's number of oscillators or something like that. But we can do it for a small situation just to get the feel of what we're getting ourselves into and why this is going to be important. So I'm going to make a table of the distribution of energy and the possible number of ways that can happen. And then I'm going to look at the total number of accessible states. So, of course, my energy units can be distributed in the following way. I can have all 6 energies in system B, or I can have them all in system A, or I can have some distribution here, which is just, will sum to 6. Now the possible ways of these configurations occurring, of course, we're going to use the same formula we used before, which is to say, if I take q plus n minus 1 divided by q factorial divided by n minus 1 factorial, that will give me the omega for each of these systems. And if I were to, so if I put those numbers in, I'm going to get numbers that come out like this. And of course, the absolute reverse on the other side. 1, 3, 6, 10, 15, 21, and 20. And if I add up all of the possibilities, I get the following configuration. For a total of 462 microstates of this system, if you will. Now notice that my biggest number, the largest number of states, happens when each of these guys have 3 units of energy between them, for a total of 6. What we're going to talk about, and we'll talk about this in more detail later, is a postulate called the postulate of equal a priori probabilities. It's an extremely important postulate in statistical mechanics, but it's one that we can't prove. We have no examples of it being disproved, and it seems to be correct. And as I say, we've never seen an example where it's not correct. But what the postulate states is that a system is equally probable to find a system in any of its, in this case, 462 possible configurations. One configuration out of the 462 is not any more likely than another. Nonetheless, you see that we have many more, well, somewhat more accessible states that have 3 and 3. So that's a more probable configuration than, let's say, 0 and 6 or 1 and 5 and so forth. But this is going to be very, very important to us as we go along. The idea of the postulate is that in equilibrium, all accessible microstates are equally probable. There's another principle that we want to introduce here, and that's called the principle of detailed balance. And that means very simply, any process that takes a system from state X to state Y is just as likely to take it from state Y to state X. So, as we see, while all 462 microstates are equally probable, the macro state where QA and QB is 3 is more probable than the others. Now, this will become more pronounced when we go to bigger numbers. So let's get more adventurous. Suppose I have 300 oscillators in system A, and I have 200 oscillators in system B, and I have 100 units of energy that I can exchange or share between those two systems. So this is a much larger number of configurations. In this case, I have 101 possible macro states. Remember, each one of these is a macro state. The number of microstates, though, is quite a bit different. So let's look at one. In the case where, let's say, the total number of microstates, if I were to do the calculation, and this would probably make your calculator blow a diode or something, microstates would be something like 9 times 10 to the 115 microstates. So you might look at this 3 and 3 example as 462 microstates is a large number, but it is nothing compared with 9 times 10 to the 115th microstates, where what we get to if we just go to 300 oscillators, 200 oscillators, and 100 units of energy to share between them. Now, if I look at the macro states that result from this, it turns out, let's say that all of the energy were in system B, and A had 0 energy. So that's one of the least likely cases to occur. If that's the case, I'll get 3 times 10 to the 81 microstates where the energy in B is 100 units and the energy in A is 0. That still sounds like a lot of states, but not compared to the total number of microstates. On the other hand, the most probable configuration, as it turns out, is that if it turns out that if QA is equal to 60 and QB then is equal to 40, that number of microstates turns out to be something like 7 times 10 to the 114th power. So this is the most likely macro state. This is the least likely. Again, the numbers are telling us something. 3 times 10 to the 81st number of microstates, that sounds like an enormous number. But compared to 7 times 10 to the 114th, it isn't all that big. In fact, the difference between the two states is about something on the order of 10 to the 33 times. You are 10 to the 33 times more likely to see a configuration like this one than you are like this one. So you have a very, in a sense, a very sharply pointed probability. Now, on the other hand, if I move from QA equals 60, on either side, the probability of that configuration drops like a rock. So a good example of this is the probability of QA being less than 30 or QA being greater than 90 is less than 1 in a million. So we have a very, very sharply peaked probability distribution. Okay, let's look at this a little bit. See if we can get a little bit more physics out of this. So let's do the following. Suppose I have suppose the system is initially, let's say that all of the energy, suppose we have a case where QA is much, much less than 60. I mean, it could even be 0. If I wait a while, and again, I'm letting the systems interact, but if I wait a while and check the system later, we certainly expect that some energy has been transferred from system B to system A, because system A had so little and system B had so much. Again, we would probably expect that there won't be anything flowing from A to B because A has so much less energy than B does. We look at this as an essentially irreversible process. We'll talk about irreversible processes in more detail later on too. But if you think about it, doesn't it sound a lot like the way heat flows? We always think about the fact that heat flows from a warmer object to a colder object, but never the reverse. That's a pretty good hint of what's coming up. In fact, that idea, heat flowing from a warmer object to a colder object, is one of the ways we state the second law of thermodynamics. We're going to expand upon that as well. We also would expect that the energy flow in this case, or when we talk about heat from a warm body, will stop when we have an equilibrium situation and the system is at its highest or nearly highest macro state, the highest multiplicity. So again, this sort of, if you thought about the thermodynamics that you studied earlier, this will remind you a great deal of what happens with the second law. The idea here is that we're going to talk about the second law in a much more fundamental way. But another thing that I want to point out up front is the second law is not an absolute airtight statement. It's more of a statement of something that is of great probability. In other words, while we can't say that it's never, never, never true that heat will flow or thermal energy will flow from a colder object to a hotter, it's just exceedingly unlikely. There's a probability associated with it, but that probability is vanishingly small. Now, we're seeing big effects even with 300 and 200 oscillators. But the fact of the matter is that imagine if we were using Avogadro's number of oscillators. These effects would be even more sharply pronounced than what we see with just 50 oscillators. That brings me to at least a bit of a digression about numbers. We kind of throw around numbers pretty cavalierly, but we can sort of think of numbers in 3 categories. I can think of small numbers, something like 5 or 82. Those are small numbers in what we discuss in statistical mechanics. I can think of large numbers, and those would be like Avogadro's number, 10 to the 20, that's a big number. I can also think of very large numbers, which would be like taking Avogadro's number, or 10 to the 10, and raising that to the 23rd power. Those are very, very large numbers. Well, as part of this digression, we need to talk about how we can handle very large numbers because they are extremely cumbersome. So when we get so huge that it becomes unwieldy to deal with large numbers, we've got to resort to a couple of tactics. One is, let's resort to natural logs. It's a lot easier. When I take a natural log of a system, I compress the system a great deal. A good example of that is I can take an enormous range of pressures in terms of what the ear can sense, many, 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 many orders of magnitude, invoke the decibel scale, which is a common log scale, And then I'm only dealing with numbers that go from 1 to about 120 or 130, threshold of hearing to the threshold of pain. Same idea applies in statistical mechanics. So we're often going to invoke things like the natural log, like the natural log of omega. We also need some better approximations when it comes to factorials. And the one that I want to talk about right now is called Stirling's approximation. I'm not going to derive it, but I'm going to make a really good plausibility argument as to why we would use such an approximation, and why we would be allowed to, I should say. So here's the actual statement of Stirling's approximation is n factorial. I can write that as approximately n to the n times e to the minus n times some factor of the square root of 2 pi times n. You might say, wow, that's a pretty bold leap of faith to just write it out that way. Well, what I'd like to do at this point is let's talk about why that might be a plausible way of expressing n factorial, particularly if n factorial is enormous. N is enormous, and thus n factorial becomes even more enormous. So the first thing, let's do this. Let's replace n factorial by n to the n. Okay? Now that's going to be too big, right? Because n factorial is n times n minus 1 times n minus 2 times n minus 3, all the way down to 1. N to the nth power is n times n times n times n times n. So this is already much too large. So I'm going to have to ameliorate that situation by doing the following. I'm overcounting that number by about a factor of e for every one of those factors. So what I'm going to do is take n to the n and divide by e to the n. And that's going to get me a little bit closer to what n factorial is. Again, it's a plausibility argument. It's not rigorous. Which means, of course, I can write this as n over e quantity to the nth power. Or if I like, same thing, I can write that as n to the n times e to the minus n. So I'm seeing this already. And the last one, it's still too large, or I should say too small, by a factor of square root of 2 pi n. But that number is going to be not terribly consequential. These numbers are going to be enormous. This number is just a small factor that I would multiply that number. It wouldn't make a heck of a lot of difference. And so for little effect, I can use this expression, or even this expression, to approximate something like n factorial, where n is a very, very large number. Take it a step further. As I say, we like logarithms to compress the scales and make it a little bit more, make it a little less unwieldy. So if that's the case, I can express the log of n factorial approximately as n log n minus n. And this is the real, well, not the real, but the Stirling's approximation that we use all the time in statistical mechanics. It's extremely useful, and you will use it, for example, in homework problems. So that's one that you may want to get used to. Okay, having said that, there's a nice use of that in the problem that we're trying to solve right now with the Einstein solid. So we can fairly rapidly, I can do this. Let's do the following. Suppose I have many oscillators, but even more energy levels. Well, if I don't do it exactly, I can write this as q plus n minus 1 factorial over q factorial n minus 1 factorial, as I've been doing. But if n is very, very large, I can say, you know, n minus 1 factorial is roughly n factorial. It's not going to change a whole lot. So I'm going to write this expression as q plus n quantity factorial over q factorial times n factorial. if I take the log of that expression, I get, of course, the log of q plus n factorial minus the log of q factorial minus the log of n factorial. Invoke Stirling's approximation, where I write the log of this as this log of this minus this, and for these expressions as well, I'm going to end up with an approximate value of q plus n times the log of q plus n minus q log n, q log q minus n log n. And what I can do next is I can approximate this. Let's look at just the first term. I can approximate the log of q plus n as the log of q plus n over q. How do I know that? Let's continue next time, and we will show you how we invoke a Taylor expansion to show this approximation, and we will continue and finish this example and move into the ideal gas.